Welcome to Module 202D, which is an introduction to parallel AC circuits. We're going to split this up into three parts, looking at resistors, inductors, and capacitors in parallel separately. The first part is to look at resistors in parallel. This should be more of a review of your first year theory. Whenever we have anything connected in parallel, this represents most of the circuits that we work on. All the separate branches would effectively be connected directly back to the source, so that makes my E my constant, and voltage is now my reference when I'm looking at the phasor diagrams. I can use my Ohm's law formula, which would be equal to I is equal to E over Z, to calculate what the total ampacity for each individual branch is. Keep in mind that with a resistive load, the R and the Z are the same value since we don't have any reactances at all. So by using Ohm's law, I can calculate that I1 is 3 amps, I2 is 4 amps, and I3 is 6 amps. By adding all three of those together, I get an I total of 13 amps. In parallel theory, the more branches that I add means I have more of a draw on my system total. So the more branches, the higher my total current is going to go. Since current and resistance are inversely proportional, when I add more branches in parallel, that also means that my total resistance is going to go down as my total ampacity goes up. So the more paths I have for current, the less my total resistance is going to be. To calculate total resistance, we use our reciprocal formula, which states that the reciprocal of R total is equal to the sum of the reciprocal of all of my resistors put together. So even though in this circuit I have a 40 ohm resistor, a 30 ohm resistor, and a 20 ohm resistor, my total resistance is only 9.23 ohms. Let's look at phasor diagrams of this circuit. Here we have four separate phasor diagrams representing each individual branch as well as the circuit total. You'll notice that the current for each individual resistor as well as the total current are all in phase with the voltage. This means that any resistive load has a 0-degree angle and a power factor of 1. The length of the phasor representing each individual current on each individual branch, if you're to add them all together, would equal the total length of the phasor representing the total current. And we can also see this mathematically, being 3 plus 4 plus 6 is equal to 13. When calculating the power in a resistive circuit, we are always going to be using our source voltage and the current of either any individual branch or our total current. In this case, we're looking at power for the total circuit. My power formula, being E times I times cosine of theta, will give me my power. It is 120 volts times 13 amps times the cosine of 0 degrees, which is 1. The value that we have is 1,560 watts. If we compare that to my apparent power formula, being E times I, in this case 120 volts times 13 amps, we also get 1,560 VA. With a resistive circuit, power and apparent power are the same value because we don't have any reactive power components. Here we have our summary sheet for our resistors in parallel theory. Remember that total resistance, we always use a reciprocal formula to calculate that. Our total impedance is always going to be equal to the total resistance since there is no reactive component to this. Total current can be used as I is equal to E over Z or E over R total. Apparent power is equal to true power. The power factor is always going to be 1, and the phase angle is always going to be 0 degrees. And this will always be true for any resistors connected in parallel. This ends part 1 of 202D. Review this video as many times as you would like, and then continue on to part 2.